Okay, let's go ahead and get started. So, before I start the lecture, I'll just make a few announcements. So, the first problem set is posted, and it's due February 8th, which is next Wednesday. So, if you want to get started on that, you can. And after today, I think we'll have covered enough for you to do 3 out of 5 of the problems, and then the last 2 you'll have to wait until after Wednesday's lecture. Any questions about the problem set? Okay, and then just a reminder, please wear a mask if you have one with you, and we'll continue wearing masks through next Wednesday, and then after that it will be up to you. And then the last announcement is that I will have office hours today for the hour immediately following class. So if you have questions or you want to get started on the problem set, feel free to drop by. Okay, so the topic for today is mathematical induction. So this is a very important method of proof for proving any statement about integers. So we'll start off by proving a theorem, which is like the so-called first principle of mathematical induction, and that's going to be like the main theorem. That's going to be the theorem that tells us basically that this method of proof works. And then I'll do an example, and then we will talk about strong induction, which is like just a kind of different flavor of induction, and we'll use that to prove part of the fundamental theorem of arithmetic, which I showed you at the end of last class. Okay, so let's jump right in and do the first principle of mathematical induction. Okay, so, hey. Okay, so what is this first principle of mathematical induction? So, this is going to tell us that the method of proof known as induction actually works, and it's going to rely on the well-ordering principle. I don't know what you could possibly be upset about. All right. I'm just going to hold on to you. Okay, so I'm going to let S be a set of integers containing some element A. And you know what, I think I want this to be a set of positive integers. Okay, so we have the set S and it contains some element A, and then we're going to suppose S has the following property. So it has the property that if any n greater than or equal to A is in S, then n plus 1 is also an element of S. Okay, so this is just a property that the set S has. Then the theorem says S contains every integer greater than a. Okay, so as long as you have some first element a, and you have the property that whenever you have some integer larger than that, then n, and then n plus 1 is also in the set, that implies that, in fact, your set contains every integer greater than or equal to a. Okay, so let's prove this statement. So I hinted that we were going to use the well-ordering principle, and what we're going to do is apply the well-ordering principle to the complement of S. So let's just start off by supposing that S is a set that has this property. So suppose okay, then I'm going to set, so we'll let S prime be equal to the non-negative integers, but we'll take away all elements of S. Okay, so this is the complement of S in z greater than or equal to 0. Okay, so I want to apply the well-ordering principle, but for that I also needed that S prime was non-empty. So let's just look at a few cases. So it could be possible that S prime is empty. But, yeah. Yeah, I'm going to change this to be non-negative, actually. So we'll adjust that statement. Yeah, thank you. Other questions? Okay, so if S prime is empty, then what does that mean? That means that S contains all of z greater than or equal to 0. And so in particular, it then also contains every integer greater than or equal to a, and so we're done. Okay, so if S prime is empty, then the proof is complete. So we'll move on to the case when S prime is non-empty. So if S prime is non-empty, then we're now in a situation where we can apply the well-ordering principle. So then S prime contains a least element, and let's call it B, by the well-ordering principle. And let's also note that B cannot be equal to A because A is in S, and so therefore A is not in S prime. Okay, so now we have this least element, and I'm going to break this down further into two other cases. So first, So this is like case 2A. So let's suppose B is less than A. So what would this mean if B was less than A? Yeah.
B is less than A, then like A, I guess, can't be 0 because then there's a non-negative integer that's less than A.
Yes, that's true. Okay, I'm going to give you like 2 or 3 minutes to discuss together how to do the proof in this case. So if B is less than A, and you can also think about what happens, so the other part of this, what happens if B is greater than A. Okay, so take a few minutes to discuss this. Okay, so I think the proof, the way that I had done this part, had an error in it. So I don't know if anyone was able to do it this way, but I have a fix. Did anyone get anywhere with this half of it? Okay, so here's my fix. So let's go back to S. What? What is this? Let's go back to S and define this to be like this. So we'll look only at integers that are greater than or equal to a, and then take away S. Okay, so then we can still, so let's just check this. So it is possible that S prime is empty, and that would mean that we are done. And then in this case, we can still apply the well-ordering principle, and we'll use this least element B. Okay, is everyone happy with the setup? Yeah.
Is S about the are also just the numbers greater than or equal to A, or are we thinking about S?
So what is S prime?
What is S not prime?
Oh, S is just a set satisfying the like hypotheses of the theorem.
But I thought, sorry, I thought that the theorem is saying that it includes all the numbers n greater than A.
Sorry, I'm having a hard time hearing you. Can you speak up?
I thought like the theorem said that S contains all the numbers greater than A, but that's why.
Okay, so the setup is we're assuming that S has this property. So if there's some number n greater than or equal to a that's in S, then also we have n plus 1 is in S. So we're just assuming that this set S has this property, and then we're going to prove that then S actually contains every integer greater than or equal to a. Yeah, okay. Good. Other questions? Okay, so now we're set up. So let's consider B minus 1. So we selected B using the well-ordering principle. So that means that B is the smallest element of S prime. So that means that B minus 1 must in fact be an element of S. Okay, so this is since B is the least element of S prime. Okay, so then using the assumption, this means that B minus 1 plus 1 is in S. So B is in S. But that's not possible because B is in S prime. So we have a contradiction. So what does that mean? That means that it was not possible that S prime is non-empty. So this case led to a contradiction. So that means that actually S prime is empty, which implies that S is equal to Z greater than or equal to A. or rather, this is what we proved. So we proved S contains Z greater than or equal to A, which is what we wanted to show. Okay, sorry about the snafu in the way that I had originally written this proof. Are there questions? Okay, so what is the upshot of this? So this gives us a strategy for proving statements about integers. So for statements that look like the property P of n holds for all integers n greater than or equal to a, where a is just some initial value. Okay, and this is called proof by induction. And it proceeds in the following steps. So the first thing that you do is called the base case. So you prove that some small integer satisfies the property. And usually the small integer is, like typically you take 0 or 1, but sometimes it's something bigger. And then the next step is that you then have to show that like the set of integers that satisfy your property has that weird condition in the theorem. So, and this is called the inductive step. So what do? You let n be an integer greater than or equal to your base case. So let's let it be an integer larger than the base case. And suppose that n satisfies the property P. Then you must use this information to show that n plus 1 also satisfies the property. And this assumption that you make when you suppose that n satisfies the property, this is called the inductive hypothesis. So basically what you've done in these steps is you've shown that the set of integers that satisfy your property is a set that the theorem is applicable to. So the first principle of induction that we just proved would then allow you to conclude that all integers greater than or equal to your base case satisfy the property. So then, like from these two ingredients, we can conclude all n greater than or equal to a satisfy the property. Where this is like your base case. Okay, so I'm gonna do, is there a question? Yeah.
So the set upon which the probability applies to must be continuous, right? It can't have gaps.
Yeah, so you'll have all of them. Mhm. Other questions? So the way that I like to think about this is that, like, suppose you have an infinitely tall ladder. So this is like, and this just goes on forever. And you have a robot. So this is your robot. And you have to teach the robot how to climb the ladder. So what are like the two things that you need to teach your robot how to do? You have to teach the robot how to get on the ladder, and then you have to teach the robot how to go from one rung to the next rung. And then, like, you know, assuming he has infinitely many batteries or whatever, he can just keep climbing the ladder forever. So that's like how I think about induction. Okay, so let's do an example. So this is like a really nice first example because it's very simple and it just like illustrates all of the ideas at play. So let's prove that for every positive integer n, we have the following. So 1 plus 2 plus, we'll add up all the numbers up to n. Let's prove that this is equal to n times n plus 1 over 2. Okay, so let's start with the base case. So what should we start with for the base case? Yeah. 1. Yeah, okay, yeah. So we'll start with n equals 1. And what is the statement saying in this case? So we add up all the numbers up to 1. So on one side, that'll just be the 1. And then we plug in 1 times 1 plus 1 over 2. And this equation is true. So that is the base case. So so 1 satisfies this property. So we're good. Okay, then the inductive step. Okay, so here's our induction hypothesis. Let's suppose that n is a number and n is greater than or equal to 1. And we already know that this sum is equal to n times n plus 1 over 2. Then what we need to show is that n plus 1 satisfies this property. So how that looks is we'll have 1 plus 2 and so on up to n and n plus 1. So we have to show that this is equal to n plus 1 times n plus 1 over 2. Okay, and then that will be our proof. So let's start by just computing the sum on the left-hand side. And usually what you're trying to do is to somehow like use your induction hypothesis, so somehow apply that to your computation. And in this case, we see that the sum in the inductive hypothesis is present right here. So we'll use the induction hypothesis, and this will be n times n plus 1 over 2, and then we add to this n plus 1. So this step is by the induction hypothesis. Okay, and then we can simplify the right-hand side. So we get n times n plus 1 plus 2 times n plus 1 all over 2. And factoring out the n plus 1, this is just n plus 1 times n plus 2 over 2. And that's what we wanted to show. Okay, so then we can conclude that by the first principle of induction, the statement that we wanted to prove is true. So I'm going to say the proof is complete. Okay, are there questions about this example? Yeah.
I just wanted to ask about induction in general. So what if the statement has like multiple variables? Would you still be able to use induction just like doing and
Yeah, so what happens if the statement has multiple variables? So it kind of depends on the situation. Sometimes sometimes one of the variables isn't like really meaningfully involved and you can kind of ignore it and just do induction on one variable, but sometimes you have to do like a nested induction. Yeah. Other questions? Okay, so now I'll talk a little bit about the second principle of mathematical induction. So this is the second principle of induction. And this is like, if you've seen induction before, this is like the theorem that lets you do so-called strong induction. In many cases, the assumption that a statement is true for one integer n doesn't readily yield a proof that the statement is true for n plus 1. And it can be more convenient to assume that all numbers less than or equal to n satisfy the assumption in order to get the statement for n plus 1. And this is like equivalent to induction. It's not actually like stronger or anything, but it is usually called strong induction. So this statement is going to be kind of similar to the first principle, but we'll let S be a set of non-negative integers containing some element A, and we'll let n be a number greater than or equal to A. And we'll suppose that S has the property that if all integers from A to n are in S, then n plus 1 is in S. Okay, so if S has this property, then the second principle of mathematical induction concludes that then S contains every integer greater than or equal to A. Okay, so this is a similar statement to the regular induction, but now your inductive hypothesis would have you assuming that all integers from A to N satisfy the property. Okay, so I'm not going to prove this one, but we will use it to prove part of the fundamental theorem of arithmetic. Are there questions about this before we do that? Okay, so let's recall what the fundamental theorem of arithmetic said. So this said that every integer greater than or equal to 1 is either a prime or a product of primes. Anyway, I just want this to be greater than 1. Okay, so we're going to prove this using the method of strong induction. So this goes as follows. So for the base case, we'll take n equals 2. And, okay, so why is this theorem true for n equals 2? Well, 2 is a prime. So it's true that 2 is either a prime or a product of primes. Okay, so that's our base case. Are there any questions about that so far? Okay, then here's the inductive step. So now, for our hypothesis, we're going to assume, so we'll let n greater than or equal to 2 be an integer. And we'll assume that for all k in between 2 and n, we have that k is either a prime or a product of primes. Okay, so that's our hypothesis, and after we've done the proof, you should look back and think about why it was helpful to assume that all numbers in between 2 and n satisfied the statement and not just the number n. Because this is the key difference between induction and strong induction. Okay, so this is our hypothesis, and then what we're going to prove is that then n plus 1 So we're going to prove that n plus 1 is either a prime or a product of primes. Okay, so here is how this goes. So let's look at some cases. So if n plus 1 happens to be a prime, then we're done. So let's suppose that n plus 1 is not a prime. Okay, so recall, just briefly, that something is a, so n plus 1 is prime if the divisors, the only divisors of n plus 1 are 1 and itself. Okay, so we're saying that this is not a prime, so that means that we need to negate this sentence. And that means that there is a divisor of n plus 1, which is not 1 or n plus 1. Okay, so let's call this divisor A. And then last lecture, we also defined what it meant for something to be a divisor, and that means that there exists a B. So that means that there exists a B such that we can write n plus 1 is equal to A times B. Okay, so what should we do in this moment? Yeah.
I guess you would show that A times B, if the A and B for integers are smaller than n plus 1, which would make them which would make them like less than or equal to n and data is equal to 2.
Yeah.
Which would then say that would make them apply integral, which basically, if like A isn't prime, it's still a product of primes. If B is prime, then it's sort of
Yeah, okay, so we want to apply the inductive hypothesis to A and B. And in order to do that, so we need to know that A and B are numbers from so we need to know that they're between 1 and n plus 1. So a divisor is automatically in between 1, well, it could possibly be 1 or n plus 1. But since A is not equal to 1 or n plus 1, B must also fall strictly within this interval. Okay, so this is automatically zoomed in. Okay, so that means that we can apply the inductive hypothesis. So A and B are each either primes or products of primes. So looking back at this expression, that also means that n plus 1 is either a prime or a product of primes. I guess it would mean that it is definitely a product of primes. So that means that n plus 1 is a product of primes. And that concludes the proof. Okay, so that was an example illustrating how to do strong induction. It doesn't come up all that often, but sometimes it is helpful to be able to use any integer in between your base case and n, and not just the number n. Are there any questions about this proof? Okay, so on the homework, you'll see a couple of examples of, or I think maybe only one example of a proof by induction. And then on Wednesday, we're going to start talking about equivalence relations. Yeah. Yeah, so all you need to do for the proof is to assume that the hypothesis is true. So this is like an assumption, and then you just want to prove that then the statement holds for n plus 1. Yeah. Okay, and that's it. And just a reminder, I have office hours right now. Okay, yeah, so like let's start with A. So we already know that A is not 1 or +1. And since it's a divisor of n plus 1, it has to be less than n. So that would put it strictly in between 1 and n plus 1. And then let's see. Yeah. You can handwrite it. Sorry? Where are your office hours? Oh, password 016. Oh yeah. If you scroll up, there's like this entire chunk of like to move here. I think we need a special
Hi, Alva. How are you? And it feels like it's almost April in terms of the semester. Okay.
like sign a blue sheet today again, right?
Yeah. Thank you for asking.
I usually do like section and subsection. Oh, yeah. It's annoying sometimes. Like,
Can't say I've ever been faithful,
Hello.
except to God.
Thanks. Just to
Never felt
distract
like
myself
anywhere
before class starts. Yeah.
fell asleep here in your arms.
Yeah, you too.
Never thought I'd fall in love. Your love's my only saving grace. You caress my heart, kiss my face. Your love's my only saving grace. Your love. Sometimes God calls out to me to come home, 'cause I feel so all alone. Then I taste your kiss, your touch, your sweet love. 'Cause I never thought I'd fall in love with you. Your love's my only saving grace. You caress my heart, kiss my face. Your love's my only saving grace. Your love. Your love's my only saving grace. You caress my heart, kiss my face. Your love's my only saving